Hello everyone. This presentation explains about both damped oscillations and forced oscillations. Um, the simple harmonic oscillations was explained in previous lecture. Yeah. So if we go with first damped oscillations. So these oscillations are due to both internal force as well as damping force. Damping force, or you can say resistance force. So compared to simple oscillations, here extra the damping force is also involved. The resistance force is also involved. So if both these forces are together responsible for oscillations, then we will say the type of oscillations are damped oscillations. And damped oscillations are characterized by, and of course these are the common characteristic features of any oscillations. But if we say a damped oscillations, that amplitude will decreases exponentially. But whereas in simple oscillations, that amplitude will never change. But here it will decreases exponentially. And regarding time period, the time period will slightly increases. I mean, in order to take one complete oscillation, it will take little bit much time compared to simple oscillations. And of course, that is due to what? A damping force. And the frequency will decreases. Of course, these two are reciprocal. Time period and frequency are reciprocal. So you can say if time period is taking much time, then frequency will definitely decreases. And the total energy, some of the energy will be dissipated. Some of the energy will be dissipated. That's why the system total energy will decreases exponentially with respect to time. And we can show this mathematically. We can show this mathematically by just writing the equation of motion and equation of motion and its solution. So now our aim is to write the mathematical equations for both equation of motion of damped oscillations and its solution. Now we'll go to equation of motion, I mean, which should be in second order differential equation form mathematically. And if you see this, this damped, as we said earlier, that this damped system is subjected to two following forces. One of them is the restoring force. One of them is restoring force, and this restoring force is proportional and opposite to the displacement of the oscillator. And if you remove the proportionality, and this proportionality is replaced with a constant, so that Fr is equal to minus Kx. And here the K is spring constant. Spring constant, right? And the second force is damping force, and this damping force is proportional and opposite to the velocity. So that Fd is equal to minus R, and where this R is damping constant. R is damping constant, and both together will responsible for this type of oscillation. So that you can write this net force as sum of both restoring force as well as damping force, right? And if you sum up them, I mean, just write the corresponding equations for these forces. So that F is equal to, for restoring force it is minus Kx, and for damping force it is minus Rb. But as per Newton's second law, this net force is responsible for acceleration in the oscillator. So that's why you can modify this equation. Instead of net force, we can write Ma. So this Ma is equal to minus Kx minus Rb. But of course, we are interested to write that in differential equation format. So you can replace this A as d2x by dt square, g2x by dt square. and this velocity v is dx by dt. And if you change these terms, so m as it is, instead of acceleration d2x by dt square, and you are just writing this minus kx to the left side, so it will be plus, not only minus kx, minus r also. So plus kx and plus r, instead of velocity you can write dx by dt. And of course this equation is in second order differential equation form, but it is better to write in standard form, because for standard form the solution is already existing. So, but in order to write that in standard form, there should be some conditions. I mean, if it should be in standard form. There should be no coefficient for this d2x by dt square. There should be no coefficient, right? So that's why we will divide the mass on both sides of the equation. And if you divide that mass on both sides of the equation, this d2x by dt square. So this will become r by m dx by dt, and this is k by m x is equal to 0. But still this is of course, so now so you can see there is no coefficient for d2x by dt square, but still it is not standard form. So in order to write that in standard form, we just modify this equation for the sake of convenience, d2x by dt square as it is, and for second term dx by dt is common as it is. But instead of r by m, I'll replace that into 2 into some constant 2b, and instead of k by m, some constant square, omega square. And this omega is natural frequency. So if you see this equation, these two equations, this omega is under root k by m. So generally this is natural frequency of the system. Natural frequency in the sense, if there is no force, I mean if that oscillations are only due to internal force. I mean now let be this is oscillator, now this is in oscillation. If these oscillations are only due to restoring force, so some frequency will be there for these oscillations. So we'll say that frequency as natural frequency. Natural in the sense no external influence is not there. The oscillations are only due to itself by itself. So that's why it is natural frequency. And one more constant is also we defined, which is 2b. And this 2b is replaced by what? So r by m. And this is coefficient. Damping coefficient. And this is, see, you can write this as a single constant like b. But for the sake of convenience, we represent it with this 2b. We'll see that little later. I mean, why it is better to write as some 2 into constant. You can write, I mean, if it is C, if it is 2 into 4, so that will be 8, right? But here we are not, I mean, just I'm taking the random values. We are not just taking like a 8 into dx by dt. We are giving this like 2 into 4. And for that little bit convenience, I mean some flexibility is there. Because of the flexibility, we just took that constant as 2 into some 4. We came to know that after giving the solution, we came to know, I mean, what would be the reason for this 2 into some constant. Right, of course, we given the equation of motion for damped oscillations. But now we write the solution. I mean, this equation 1 is the second order. I mean, I will rewrite that d2x by dt square plus 2b dx by dt plus omega square x is equal to 0. Now, for this standard second order differential equation, the general solution will take in this form. And the general solution is, of course, uh, x is equal to a to the power of alpha t. What does it mean? Instead of x, if we substitute this in this second order differential equation, the result will be 0. That is meant by solution. And of course, here that a and alpha are some constant. I mean, we are saying this is arbitrary constant because here that some constant should be there, but we don't know that value. So that's why we generalize like a constant. And that's why it is arbitrary constant. We don't know that exact value for the system right now. So that it is called as what general solution. Now we'll try to make this exact solution just by just calculating the a and alpha value. If you are able to calculate this a and alpha values, so that the general solution is converted to an exact solution. So in order to make that, we need to differentiate this equation two times because it is second order. So now if you take that first derivative, a is, we already said this is constant, so at a as it is, and e to the power of alpha t differentiation is e to the power of alpha t, and differentiation of this alpha t is alpha. So this is first derivative, and if it is second derivative, I mean just we need to differentiate this dx by dt, so that a alpha as it is, a alpha as it is, and if we differentiate that a alpha as it is, e to the power of alpha t differentiation is e to the power of alpha t, and alpha t differentiation is alpha. So the final result will be a alpha square e to the power of alpha t. So now we'll substitute this equation 2, equation 3 and equation 4 in this equation 1. So from all these equations, we are substituting this 2, 3, 4 in equation 1. I mean from this 1, 2, 3, 4, we can see instead of d2x by dt square, instead of this d2x by dt square, we'll write a alpha square e to the power of alpha t. A alpha square e to the power of alpha t. You can see here. And 2b is as it is. 2b is as it is. But instead of dx by dt, instead of dx by dt, we'll write a alpha e to the power of alpha t plus omega square is as it is. But instead of x, a e to the power of alpha t. So now in these three terms, in these three terms, if you observe, a e to the power of alpha t is common. So just common this a e to the power alpha t from these three terms. If you comment that, the remaining will be alpha square plus this 2b alpha and omega square. So the result will be a e to the power of alpha t is common. So that alpha square plus 2b alpha plus omega square is equal to 0. Now this is like a into b is equal to 0. So either a must be equal to 0 or b must be equal to 0. But this a e to the power of alpha t cannot be 0. This cannot be 0 because this is our solution we consider. So if it is becomes 0, solution is meaningless. So definitely the second term should be 0. I mean alpha square plus 2b alpha plus omega square is equal to 0. So the second term must be 0. Then this equation seems to be like a quadratic equation, like ax square plus bx plus c is equal to 0, and the roots for this quadratic equation is minus b plus or minus under root b square minus 4ac by 2a. So we just apply this solution for equation 5. If you apply that, so this alpha will be equal to, so instead of b, here it will be 2b. So minus 2b plus or minus under root 2b whole square minus 4a square, and 4ac. Here the coefficient of small x, I mean alpha square is 1. So 4 omega square by 2. And here 2b whole square is 4b square. So that within the root you can common 4. Within the root you can common 4. And you can see here. So we will try to write that minus 2b plus or minus under root. So here I will common that 4 b, sorry, if it is common 4 and if you write that out of the square root it will be 2. b square minus omega square by 2a. Now again you can common these 2 for both the terms, so that 2 will be cancelled. So the final value for alpha, I mean final solution for this quadratic equation will be minus b plus or minus under root b square minus omega square. So this is the roots, two roots, possible roots for alpha. And if you write the two roots individually, one is with plus and one is with minus. I mean alpha one is minus b plus under root b square minus omega square, and alpha 2 is minus b minus, here the change, under root b square minus omega square, right? Now we take a linear combination of both the roots, and this all x is equal to x1 plus x2. so, so this is x1, I mean a1 exponential minus b plus under root b square minus omega square of t. So if you replace that plus with minus, that will be the second root, a2 exponential minus b minus under root b square minus omega square t, right? Because our solution is x a e to the power of alpha t. So now this, instead of alpha, we are taking both alpha 1 as well as alpha 2, right? Now we need to analysis this solution a little bit in detail. And for that analysis, the major factor will be this particular term. And in both first term and second term, the major factor will be because of this under root b square minus omega square. Because this particular may have broadly three possible values, right? So now we'll try to see the analysis of the three possible values, and we'll understand what is the role of this particular value. And if you see, first we'll take the first condition. I mean this x a1 exponential minus b plus r minus under root b square minus omega square of t, right? Now we are talking about this term. I mean the three possible conditions are either this b square may be greater than omega square. The second possible condition, this b square may be less than omega square. And the third one is b square may be equal to omega square. So these are the three broad conditions. So we'll see each and individual. Now out of these three, now we are choosing the first one. The first one, which is let b. If b square is greater than omega square, what may be the result? Right? So b square is much greater than omega square. I mean we are taking this condition. B square is much greater than omega square. So now generally we call this condition as over damped condition. See, by the condition itself it is saying this resistance force is much more compared to natural oscillations. That's why it is over damped. Now in that over damped condition, so if b square is much greater than omega square, then definitely this under root b square minus omega square value will be real value, and it definitely it will be less than b. Then second step, so if it is, I mean if this total value is less than b, then both minus b plus under root b square minus omega square and minus b minus under root b square minus omega square, I mean in this equation 6, both will be negative, because we already said this is less than b. So both terms will, final value of both the terms will get negative, right? So if both are negative, what does it mean? So the position of the oscillator is decreasing with respect to time because both are negative. In what way they are decreasing? They are decreasing exponentially. They are decreasing exponentially. But however, however, this particularly this second term, see this is with more negative value. This is more negative value. So the position of the oscillator will decreases very rapidly, more rapidly because of this second term, because this is more negative. And we can analyze the decrement of position of the oscillator due to damping due to this first term, first factor, because it is little bit negative. So, but however, that amplitude will reduce it to zero. I mean, that oscillations will come to equilibrium position very fast, very fast, because both the terms are negative. And this type of over damped condition is generally we can observe in if oscillations are in a thick thin medium, sorry, thick medium. I mean high density mediums like thick oil. So high density medium oscillations are generally over damped condition, damped oscillations. Right? Even we can observe that graphically. So this is because of first term. This is because of first term, where this amplitude is decreasing a little bit slower, right? And this first term, I mean this red graph is because of what? More negative value. This is this position of the oscillator, I mean displacement of the oscillator decreasing very rapidly, right? And the second possible condition is critical damped condition. I mean the second possible value, b square is equal to omega square. But here instead of taking exactly equal, nearby, let be they are nearby. I mean the damping force and the natural frequency values are nearby. So definitely if they are nearby, so that under root b square minus omega square will be definitely not equal to 0, but this is having very small value. The difference is very small because you are taking this b square and omega square are very near. So this value will be very small quantity h. So that's why we'll say let be under root b square minus omega square is a small value h. So if it is small value h, then the equation 6, I mean x is equal to a exponential minus b plus or minus under root b square minus omega square. This was equation 6. So now this equation will change to, see here, two roots are there, plus or minus. The first root, a1 exponential, is minus b as it is minus b as it is. Instead of this, plus h. One possible root is plus h, and second possible root is minus h, right? And if you observe this equation, this exponential minus bt is common in both the terms, right? I mean, if you write this in little bit in detail, this equation will be like this: x is equal to a1 e to the power of minus bt and e to the power of ht, and this is a2 e to the power of minus bt and e to the power of minus ht. Now this e to the power of minus bt is common in both the roots, so just common that e to the power of minus bt. The remaining terms will be what? a1 e to the power of ht and a2 e to the power of minus ht. So here it is, and then we just given the expansion of e to the power of ht. I mean e to the power of x, let be e to the power of x exponential function. Its expansion is 1 plus x plus x square plus x cube plus and so on. And if it is e to the power of minus x, alternately plus and minus. So First term is plus, and second term will be minus x plus x square minus x cube and so on. But however, you are neglecting these higher order terms. You are taking only the first order terms. So if you neglect that, and if you replace that in this equation, e to the power of minus bt as it is, this a1 is as it is. We are taking only the first order, so 1 plus ht and so on. And here a2 1 minus ht. The purpose of neglecting the higher orders is because we already said this h is very small value, right? Let be h is 0.1. Even it is bigger in damped oscillations point of view, but let be will consider h is 0.1. Then this higher order h square will be 0.01 and h cube will be 0.001. See, as the order is increasing, its value is decreasing furthermore. So higher the order of this h, smaller will be its value. That's why we are ignoring this. So that's why we are taking only the up to first order only, right? And if you see again, there will be 1 plus ht and 1 minus ht. We can do common something, e to the power of minus bt as it is. Here the first terms a1 and here a2. So a1 plus a2 plus, and here ht is common in both. This ht is common in both. So if you common that, so a1 minus, here it is with minus, so a1 minus a2. And however, at the beginning itself we are saying that a1 and a2 are constants. So addition of constant and subtraction of constant both will give the again constant only. So I'll write that in simple form. Instead of a1 plus a2, we'll write that as small p, some constant. Instead of a1 minus a2, the subtraction of two constant is also constant. We'll represent with some q. So now it is in like a simple form. So x is equal to e to the power of minus bt of p plus qt. So this is a final solution for critical damped condition. And if you observe this solution, x is equal to e to the power of minus bt of p plus qt. If you do analysis, so here the displacement of the oscillator depends on time, of course, and that is governed by two factors. One is e to the power of minus bt, which is exponential behavior, and p plus qt is the second term, which governs the position of the oscillator, which is a linear behavior, right? So now this equation is having two terms. Dependency of time is in two ways. One is linear factor p plus qt, and exponential factor e to the power of minus bt. But here this is positive because this time is with positive, and this is negative because this time is with negative. So I mean the physical interpretation is the displacement of the oscillator will be increases because of this second term, but at the same time the displacement of the oscillator will decreases because of this first term, right? What does it mean? So when that damped oscillation starts, because of this factor p plus qt, at the beginning, I mean at initially, the displacement of the oscillator will increases. But gradually, as time is going on, as oscillations are proceed, because of this exponential factor e to the power of minus bt, that oscillations will decreases. But however, this e to the power of minus bt, I mean exponential behavior will dominates on linear behavior. And if you see the graph, so this is like y equal to mx plus c, I mean p plus qt, and this is e to the power of minus x, right? At a particular value of time on I mean e to the power of minus t let me, at a particular value of time. So randomly I'm checking, randomly I'm taking this value. So if you compare to, if you compare, I'll take this here. So if you compare both y-axis, see here. So this y-axis is a little bit larger. What does it mean? This e to the power of minus t is dominating p plus qt. So one factor is makes increasing the displacement, and second factor is making decreasing the displacement. But however, finally, the resultant will be decreases. I mean, what does it mean? This e to the power of minus bt will dominates on p plus qt. So finally, the displacement of the oscillator will decreases gradually, exponentially. So this type of condition, I mean critical damped condition, is generally observed in measuring instruments like ammeter and voltmeter. So where you can see when you are when you switch off the disconnecting these particular meters, voltmeter, ammeter, it will come to zero very fast. It will come to zero very rapidly. I mean even this decrease in displacement even more rapid compared to previous condition, which is over damped condition, right? And third one, the third possible condition is under damped. So condition itself saying that the damping constant is less compared to omega square. So if b is much less than omega square, so definitely the square root value will be what? Imaginary value, because the result will be in minus value. So if it is imaginary, just see here, under root b square minus omega square. So we'll do one thing. We'll take minus 1 as common in this. So square root of minus 1 will be what? I. And if minus 1 is common, omega square minus b square. So for the sake of convenience, we will consider this omega square minus b square as beta. So there is no much logic for this, for the sake of convenience, right? Because we are going to write this omega square minus b square repeatedly and repeatedly. So to reduce our stress, just we are taking this as beta, right? So there is no much logic. This is for only convenience. So now this under root b square minus omega square is finally what? I beta. If it is I beta, then now this equation 6 will change to, see here, a1 as it is, exponential as it is, minus b as it is. This value is I beta. So I beta of t plus, okay, here it is minus I beta. Only changes minus I beta. And here also we can common something. If you observe this equation, here also we can common. I mean, if you write this in extended way, x is equal to a1 e to the power of minus bt and e to the power of I beta t. The second term, a2 e to the power of minus bt and e to the power of minus I beta t. So here e to the power of minus bt is common. E to the power of minus beta is bt is common. If you common that e to the power of minus bt, remaining will be a1 e to the power of I beta t plus a2 e to the power of minus I beta t. Right now, of course, this equation is okay, but it is in a little bit complicated manner. I mean, it is not easy to use to solve the underdamped condition solutions. We'll try to make it a little bit simpler so that we can apply that easily for any conditions. So in order to make this solution easy, we'll do one thing. We'll just write the expansion of e to the power of I beta. I mean, this is like e to the power of I theta is cos theta plus I sin theta. Here instead of theta, what we are having beta t. So just here, e to the power of minus bt as it is, a1 is also as it is. Now just write the expansion of this e to the power of I beta t. It will be cos beta t plus I sine beta t. So second term will be as it is except this minus. Instead of plus it will be here minus. Now we can see two two real terms and two imaginary terms. This is first real term and this is second real term, and both these are imaginary terms. So we group them. We group them both real terms separately and imaginary term separately. If you group them, e to the power of minus bt as it is. If cos beta t is common, a1 plus a2. And next, here I sine beta t is common, so that it is a1 minus a2. And however, again, a1 a2 are constant, but they are first time it is sum up and second time it is subtraction. So addition or subtraction of two constant, again the result will also be constant, right? So we'll write that constant in convenient way, like e to the power of minus beta bt as it is. Here cos beta t is as it is. Instead of a1 plus a2, we are replacing that with a sine beta. And next, sine beta t is common. I of a1 minus a2 is replaced with a cos theta. If you do that modification, now this is like sin a cos b, cos a sin b, sin a cos b plus cos a sin b, and this is expansion of what? Sin of a plus b. Here instead of a, beta t, instead of b, theta. Right? So final result will be what? E to the power of minus bt a. So this is coefficient for sine a e to the power of minus bt sine of beta t plus theta. Right? So these are the changes that we are given. I'll explain. These are the changes. Right now, if you see, uh, this is the final solution for under damped condition. X is a e to the power of minus bt sine of under root omega square minus b square t of t plus theta, and this will be the behavior of this equation. Now just see here, what does it mean? The position of the oscillator, when the displacement of the oscillator is changing, of course, with respect to time. In what way it is changing? It is changing sinusoidally. It is changing sinusoidally. So that's why see here, sinusoidal behavior is there. Sinusoidal behavior is there. But that amplitude is not constant. Because whatever the term before that sine function is amplitude here. So just here, compare with simple oscillations. X is equal to a sine omega t. So for this we just given the graph like this, that the amplitude will never changes. The amplitude will be remains constant. This is for simple oscillation. But because this a is constant. But now here a e to the power of minus bt is amplitude for under damped condition. This amplitude is decreasing with respect to time. So that's why that amplitude is not constant. It is shown, it is decreased. In what way it is decreased? Exponentially it is decreasing. Right? This is a graphical representation of under damped condition damped oscillations. Now if we see the graphical representation of the three conditions, I mean I mean the first condition is um, b square is much greater than omega square over damped condition. The second one, b square is almost all equal to omega square, critical damped condition, and b square is much less than omega square. This is under damped condition, right? So this is under damped condition. B square is much less than omega square. Here instead of omega square it is written 4mk. However, so this blue color line is under damped condition, and see there compared to rest of the two lines that amplitude, I mean the position is decreasing gradually. Gradually it is decreasing. I mean coming to zero little bit slower compared to rest of the two. But whereas the this green color line, I mean this is for over damped condition, right? It is also decreasing, but compared to under damped condition little bit faster, right? Under damped condition is very slow. I mean decreasing its position very slow, and it is very slowly. Little bit faster in case of over damped condition. But whereas the third condition, critical damped condition, that is shown with red color, this is much more, I mean rapidly it is decreasing its amplitude. See that it is coming to zero very rapidly. So this graph is indicating the uh, effect of, I mean relation between b square and omega square, three possible conditions simultaneously with this graph, right? So what is the conclusion? That amplitude, of course decreasing, amplitude is decreasing in case of, amplitude is decreasing in case of damped oscillations. But the order of decreasing, I mean the speed of decreasing is as follows. So decreasing slowly when it is under damped, under damped, right? This b square is much less than omega square. A little bit faster in case of over damped, over damped. I mean this b square is much greater than omega square, and it is very faster in case of critical damped, critical damped condition. What does it mean? This b square is much greater than omega square, right? And these underdamped oscillators are practical oscillators generally. So that is about damped oscillations. Now we'll go with the third type of oscillations, which are forced oscillations. And compared to damped oscillations, the difference is, see here, this internal force is common, this damping force is common, the extra force, the third force is external periodic force. So this is added, right? See, and this force must be not at a once, it is periodic in nature. I mean, it should apply that continuously and that to be periodic. So the type of force is like you are applying some amount of force, you are applying some amount of force, but it should be periodic in nature, right? And we'll see the characteristic features, how these forced oscillations are characterized by. So this amplitude, that amplitude we cannot say it will increases or decreases, but it will definitely increases at the condition of resonance. We'll see that later on. In what does it mean by resonance? So only at resonance condition that amplitude will definitely increases. In other cases that depends on the damping and the external force. So it is not fixed that it will increases. It depends on what damping and frequency of the force and the time period. Time period will also be not like it will increases or it will decreases. That depends on again what the driving frequency, the external periodic force frequency, right? And the frequency of oscillations. And that will also be not fixedly it will increases or decreases. That depends on what the driving force frequency and then it is independent of natural frequency. The total energy will be remains constant, but at the condition of resonance it will be maximized. We'll see that in detail. I mean we are now we need to explain mathematically all these four conditions what we done in case of previous damped oscillations and simple oscillations. But for that, first we need to write the equation of motion. So to write the equation of motion, first we'll define all the three forces. Right, the first force is a restoring force, and of course it is proportional and opposite toward displacement. I mean this F R restoring force is equal to minus kx. And the second force, which is frictional force or resistance force or damping force. So this damping force Fd is proportional and opposite to velocity of the oscillator. So that's why it is minus Rb. And the third one, the external force, more exactly it is a one-time force. It is periodic force. It is periodic force. So the periodic nature is generally explained with trigonometric, with what trigonometric function, sine function. So that's why it is capital F sine Pt. So what does it mean? This is the force you are applying, and here the maximum force is capital F. And this is amplitude, but here the function is for force. That's why it is maximum force. And what is the angular frequency of this force? Let be small p. Linear frequency is p by 2. Right now, if these three forces are responsible for the oscillations, now we'll sum up that. We'll calculate the sum of these forces. What does it mean? Now this net force is equal to what? Fr restoring force plus dissipation force plus external periodic force F sine Pt. And this net force is responsible for acceleration in the oscillator. So if you use the Newton's second law, this F net can be replaced with what? Ma. Now we'll write this in differential form because equation of motion should be mathematically in second order differential equation form. So that's why we write that. If you write that, instead of acceleration, we can write d2x by dt square is equal to minus kx as it is minus r. V is velocity of the oscillator, so it will be dx by dt and f sine pt. Now we'll write this both minus negative terms left side of the equation. If you are writing that, and write this minus kx minus r dv by dx by dt at left side and divide with mass. So dividing with mass is for the sake of what? To write that in standard form. So if you are able to do that, d2x by dt square, because this mass will be cancelled if you divide the mass on both sides, remaining k by mx, and here r by m dx by dt is equal to capital F by m sin pt. Still it is not in standard form. The standard form will be d2x by dt square plus instead of k by m, sorry, instead of r by m, 2b dx by dt, what we done in case of damped oscillations in previously. And k by m x is omega square x. Here the capital F by m is taken as small f, right? So these are the replacements. Instead of 2b, r by m. Instead of omega square, k by m. And instead of capital F by m, small f. So these are the modifications taken to write that in standard form. And so now for that format second order differential equation, the general solution we take in this form. X is equal to a sine of pt minus theta. And where this a and theta are arbitrary constants. What does it mean? Now we need to find what is the value of a and what is the value of theta. Now this is our aim right now, so that this general solution will turns to exact solution. And for that, of course, like we done in case of simple oscillations and damped oscillations, this has to be differentiated two times. So if it is differentiated first time, first derivative will be a constant as it is. Differentiation of sine theta, I mean sine of pt minus theta is cos pt minus theta, and differentiation of pt is p. So ap cos of pt minus theta. And if you differentiate this again, second derivative will be ap as it is. Differentiation of cos is minus sine. So here minus sign is obtained. So minus AP sine of PT minus theta, and differentiation of PT is again P. So that's what it is A P square. So now we'll substitute this equation 3 and equation 4 in this equation of motion. And if you are able to do that, just see here. This d2x by dt square as it is we what we calculated from equation 4 minus AP square sine of PT minus theta plus here the 2 be written as it is, but instead of dx by dt, see this equation 3 to be AP cos of PT minus theta plus omega square is taken as it is, but instead of x, equation 2. So omega square A sine of PT minus theta is equal to what? The right side of the equation f sine PT. Now, in order to solve this, we are taking some considerations. I mean, we are doing some mathematical operation that is purely for to make this equation simpler. And what that considerations are? Just here, the first step. The first step is see this first and third term, left side. First and third term, sine of pt minus theta, and here the sine of pt minus theta with a is common. So make this a sine of pt minus theta is common for both first and third. What will be the result? Plus omega square minus p square. So omega square minus p square of a sine of pt minus theta. And the second term is as it is, no change. But at right side, I mean, as I told, for the sake of convenience, what you are doing, small f sine pt, we are subtracting and adding the theta. I mean, f sine of pt minus theta plus theta. So if you do that, this is like sine of a plus b. So instead of a, it is pt minus theta. So that expansion of sine of a plus b is what? Sine a cos b plus cos a sine b. So we'll write that. We'll write that expansion. Right. So now this left side of the equation is as it is. There is no change. F sine of a plus b expansion. Sine a cos b. I mean sine pt minus theta cos theta. And cos a sine b. F cos of pt minus theta plus sine theta. Right. Where we end the previous slide here. Left side of the equation, omega square minus p square of a sine of pt minus theta plus 2b ap cos of pt minus theta. At right side of the equation, f sine pt of minus theta cos theta and f cos pt minus theta cos theta. And if you observe both the sides, if you observe that sine of pt minus theta at left side and sine of pt minus theta at right side. Similarly, cos of pt minus theta at left side, cos of pt minus theta at right side, both are with equal. So that's why we will compare the coefficients of both these terms. If you compare that, if both are equal, what does it mean? What does it mean? This left side, this coefficient of the sine of pt minus theta at left side is a of omega square minus p square will be equal to what? F cos theta. Similarly, the coefficient of cos of pt minus theta, left side coefficient is 2bap. Left side coefficient is 2bap. And right side coefficient is f sin theta. So we just compared both the coefficients, both at left side and right side. Now we'll try to solve that because our aim is to solve the a and theta. Accordingly, we are going now. Now square and add both equation 5 and 6. Square and add both equation 5 and 6, both at left side and right side. If you do that at left sides, so if you are squaring this, a square of omega square minus p square whole square, and left side of this 6, which if you square this 4b square a square p square, which is equal to f square cos square theta plus f square sin square theta. And of course, cos square theta plus tan square theta is 1. So that's why the final result will be f square. But our aim is to write the equation for a now. So and see here it is a is common. If you common that a, the result will be, I mean a square is common. Result will be omega square of minus omega square minus b square whole square plus 4b square p square, which will be equal to f square. Now I can write the equation for what? A square. So this entire term can be written as what? This entire term can be written as denominator of this f square, right? So the final value of a will be, I mean if you square root on both sides, f by under root omega square minus b square whole square plus 4b square b square. So this is the value of a. So this a is calculated. Now we go with theta. So for that, just do the equation 5 by equation 6 on both sides. If you do that, at right side, f sine theta by f cos theta at right side. And at left side, 2b ap by a of omega square minus p square. Of course, this a and a will be cancelled. This sine theta by cos theta is equal to tan theta, and this f and f will also be cancelled. And if you do all the modifications, tan theta is equal to 2bp by under root omega square minus p square, right? So theta will be equal to what? Tan inverse of this value. Now we calculate even the theta also. Now see the solution. So this is the equation of motion of forced oscillations, and its solution will take in this form. But it is general solution because we don't know the value of a and theta. But by differentiating and substituting in equations, we are able to find this a and theta. So if you apply this, the exact solution will be in this form. So instead of a, we will write this. Instead of a amplitude, we will write this. And instead of theta, we will write this. So now this will be the final solution for forced oscillations. Right, now we'll take the special case, the concept of resonance. So generally the concept of resonance is defined if two frequencies are same. Is a case where two frequencies are same, are matches, right? And in forced oscillations, there are we define we define two frequencies. One is omega, natural frequency, natural frequency in the sense there is, let be, if there is no damping force and external periodic force, the frequency of the oscillations, I mean only due to internal force, right? The frequency of oscillation is omega, natural frequency. And here we define one more frequency which is p, I mean frequency of force, frequency of force p. This is maximum force. So this frequency of force is p. Right? Now just see the graph. Now let be some oscillator. Let be some oscillator. We'll take some oscillator. If there is only internal force, the frequency of oscillation is omega, which is natural frequency. Now for this oscillator, now you are going to apply force, periodic force. So that periodic force may be like this. Let be this is first force. That force may be applied in this way also, right? This force may be applied in this way also. So what is the difference in these three types of forces? The small p, the frequency of force. I mean, how many number of times that force is applied in 1 second. Here the frequency force is less. I mean, it's over lower values. Here the frequency of force is very large, I mean at higher values, right? And it is moderate. So somewhere this frequency of force P may be equal to what? The natural frequency of the oscillator. So out of these all the possible values, so somewhere the frequency of force will be equal to natural frequency of the oscillator. Sorry. At that force of P, where this is equal to omega. that oscillator is having the maximum amplitude when compared to any other frequency of force. It will displace us with the maximum value. So where that amplitude is getting maximum, that is resonance condition. And that resonance condition is possible when when the frequency is equal to, I mean, this external periodic force P frequency is equal to natural frequency of the oscillator omega. Then we will get the maximum amplitude. That is the concept of resonance, and this is condition for resonance. Condition for resonance. Right? Even we can find that value. We can generalize its value by just doing this just simple mathematical operation, right? So now we are dealing with what amplitude. So first we will take the equation for amplitude. Just in previous slides we given this. That amplitude of the oscillator is f by under root omega square minus p square of square plus 4b square p square. And what is our condition? Now this amplitude should be maximum. This is condition for resonance. This amplitude must be maximum, right? So if it has to be maximum, definitely this denominator should be what? Minimum. If it is minimum, then because they are reciprocal. So if this denominator is minimum, then definitely this amplitude will be maximum. And in differentiation, what is the condition for minimum? Its first order must be 0. I mean, this is the mathematical condition. Let be this is some function. So I'll take some function graphically. I do like this. Let be this is the behavior of function. The first order derivative at maximum and minimum is 0. The first order derivative of maxima at maxima or minimum will be 0. Right? Now what you are saying, if this is minimum, amplitude is maximum. So I mean it has to be minimum. If it is minimum, then its first order will be definitely what? 0. So that's why at minimum this d by dp of omega square minus p square whole square plus 4b square b square will be equal to what? 0. Right? And if you differentiate that with respect to p, so, right? So this differentiation of this first term. So first differentiation for the square 2 omega square minus p square, like differentiation d by dx of x square is 2x, right? So 2 omega square minus p square, and differentiation of this minus p square is minus 2p, and 4b square as it is, differentiation of p square is 2p. And if you observe here, this 2p is common in both. 2p is common. If you make this 2p is common, minus 2 of omega square minus b square plus 4b square, and this 2p cannot be 0 because this is the frequency of force, frequency of periodic force. We are applying that continuously, so this cannot be 0. So the second cause, the definitely the second will be 0. I mean minus 2 of omega square minus b square is equal to minus 4b square. This will becomes definitely 0. So if you simplify this, omega square minus b square is equal to what? 2b square. So that the p will be equal to, I mean omega square minus 2b square will be equal to what? P square. Then this p will be equal to what? Under root omega square minus 2b square. So this is the condition for resonance. So what should be the frequency of forced oscillation? It should be omega square minus 2b square. Right? Thank you.